Well, hello everyone. Today we're going to be exploring transport. We are currently in, I love to write it. Learning hours with Boy Juan. All right. So from some students, I got a request to do an example in which we have an inclined plane. So that's what I'm going to do today. All right. So first thing, so in this exercise, we have a big hand plastic fluid. So from just this first sentence, what can we conclude with the fluid is Bingham without looking at the well, you can think about it while I'm writing the exercise. Hmm. It's bigger. Looking for an answer that is based on reality. You got it?
Is it like fluid and solid?
Yes, it is fluid and solid. Hello, how's it going? So working on a problem that is on an inclined plane, as you can see.
Okay.
And I was asking Paul about if we know that this fluid is behind plastic, what would that mean in terms of the shear? And before that, well, that's cooking. If we look at this shear over here, what would be the subscripts for this shear? Remember that you have
The Z.
I is the plane and J is direction.
Is it tau VX or ZX?
Vx. So you're saying that it's in the Z plane?
Mhm. Yeah.
Okay.
Oh wait. Yeah. So XZ. No. Or is I guess it's an X. Well, what is it?
Which direction is it? This tau.
Went up. Oh, it's going down. Oh, it's on.
Okay. And it's going down. That will be the direction. Is equal to what? These are my friends of reference. I have C, and this is X. If it's going down, or we had it this way, it's going this way. What would be J?
It would be Z.
Yes. So we have Z. But before that, we have a plane that is acting on. And why, let's say in this case, why it's going like outside of the board.
So. Is it the Y plane?
No, it's not the
X
Y.
plane. Wait,
The X.
X.
Mhm. To make sense?
I see it, yeah.
Yeah.
Because basically it's going this way. It's intersecting X.
Yeah, uh-huh.
But it could be going up, down, outside, but then that's what Z comes in and tells you, okay, it's going this way. X, let's see.
And why would it be going in the downward direction? The shear.
Why?
Yeah, instead of like against.
Because the gravity, like the fluid is moving due to gravity. So the only movement this fluid is getting, which is like going this way, is due to gravity. So since we have in this plane that this it's a solid phase, the only way that it has is going down this way, like a slide in a water park.
Yeah, so like the velocity of the fluid would be going down as well, right?
Correct.
And so the shear goes with in the direction of the velocity as well.
Yes, one. I mean, you have two shears. You have this one, which is XZ, and depending on this, so this distance over here is delta X, and we define it as I think that's delta. Delta. Oh, this Greek letter. So this Greek letter is equal to delta X. So it's basically this shear is going in the X plane, Z direction, and it's in the surface delta X, which is that row. I don't know what letter is that. Okay. So similar to the homework, we have some assumptions. We have, oh yeah, I was talking about the BME class. So, hello. So what I was looking for is that we describe the shear as yield stress plus over shear rate. Which is basically what or this like part of the problem is giving us. This is a relation or reality. Right? You see, when you're reading this type of problems, you have to dissect them. As much information you get, you start, okay, Bierman, this is a shear. And then after we do some derivation, we're gonna actually need this in order to solve the actual problem, right? So the first assumption is steady state. What does that mean? To be in a steady state.
That there's no accumulation.
Correct. So this means, or is equivalent saying that accumulation is equal to 0. Great. We have it's like an incompressible fluid, meaning that the density is constant. Their assumption is there's no pressure change. So pressure change is 0. So this gravity vector is constant. Fourth assumption. So F is equal to a constant. Okay. Fifth. Oh yeah, one of the assumptions says fluid moving in, hello,
Oh, you're Ellen.
yeah, see direction. Thank you. 6. Neglect adjectives. Do you have a question? No? Good afternoon, Dr. Jackson. How's it going? You gonna be our seminarist today?
No, but I'm here for the one later.
Shear rate fluid. Okay, so but going back to your question, one of the assumptions is that the shear it's going to be happening in this interface over here, which is air. And then this one that is fluid. Right? And it's happening at, so shear happens at x equals 2. You know what this letter is?
Is it delta?
Is it delta? Oh, delta? All right. Good to know. This means that the vector velocity is equal to 0, 0, v, z. Right? And well, we said that the fluid is plastic. All right. So what is the first thing that we did today? We're talking about something about momentums, summation of forces. So what do we know? You can ask questions. You can tell me, no, I don't know what's going on.
Would it be like the summation of forces and the
Let's start there. I like that. So we have conservation of momentum. So sum of forces.
is equal to like accumulation?
Yes, sir.
Plus the rate of momentum in minus out.
I think you got to flip.
Oh, minus the rate of momentum out or
No, I think it's plus out minus in. You check that with the notes? I'm pretty sure it's like that.
yeah.
Yeah? All right. So from all this information, what can we do something here? Start crossing stuff out. I have a red chalk. I want to cross stuff.
Accumulation.
Yes.
Steady state.
What do I do with this? Why?
Is it steady state?
Correct. And what does it mean to be a steady state? You gave.
Accumulation is 0.
That's it. Simple as that. All right. So we have basically momentum out minus momentum in, but we know something about velocity and mass, right? Says the velocity. We write it down. Yeah. So I forgot to put that. And constant. Okay, something that we didn't go in class, but I want to reiterate here. And let's do a cloud. This is us thinking. We gotta define momentum. So we know momentum is equal to mass times velocity, right? And we have momentum L minus momentum N, right? So we have, but we have rates. So we know that this is a mass rate times velocity, right? But what this is telling us is since the accumulation is 0, we know that everything that is going in is going out, right? So that means that the mass so the mass flow rate that is going out must be equal to a mass flow rate of what's going in, correct? Basically a direct something that we can infer from the information we got. Right? Else, also, we know that the velocity is constant. So the velocity out is equal to the velocity in. Yes? So given this information, can we do something else here?
The
Mhm.
rate of momentum, or
Uh-huh.
what is that? Right.
This moment,
Momentum, yeah. That's gonna cancel each other out.
correct. You guys see that?
Yeah.
Yeah? What about you, Steven? You see it?
But like, I'm just looking at the equation.
Yes.
So how does the rate of momentum equal each other?
How?
Yeah,
Okay. So we start here, this momentum,
Yeah.
right? So mass times velocity. All right. We know in the one hand that the velocity is constant. So the velocity of the momentum going in is going to be equal to the velocity of going out of the fluid. We know that it doesn't vary with respect to z, so it's always the same. Remember, the profile is going to be always the same, so it won't vary. So we can say that the velocity going out of the liquid is the same as going in. You get that?
yeah.
Awesome.
And what is that is from the assumption,
This one.
5?
Yeah.
So it's 5, that is.
Yes.
That one.
Mhm.
And the homework, he doesn't,
Go to the homework. I have it here.
yeah, it doesn't specify that it's like constant, but how can we, I guess infer that's constant?
Let's see. So we have steady state, incompressible, no pressure, changing in direction, gravity vector as in direction noted, the figure, and it's constant. The fluid moving in the z direction, thus the velocity vector is Vz. Neglect edge effects and shear fluid can be assumed to be 0. How can you assume the velocity is constant?
If it's,
I mean, yeah,
if it's steady state, wouldn't like the acceleration be 0 also, and then like your velocity would just be constant? Cause I think when he like makes like the rate of momentum equal to each other, he just always uses like the first like steady state
Mhm.
to make them equal to each other.
Well, in class, no, I think he was talking about the number 5
Oh, okay,
today.
okay.
So in this problem, yes, in this problem, exactly, literally we don't have this. I just added it. Make it easier. But with the question that you ask, I'm trying to see what we could say about this. Because basically what we're saying is so far that the momentum going out is equal to momentum going in.
I think in class today, he might have used 1 and 5. Both of those assumptions.
Well, steady state means that the accumulation is 0. But why is it? Because everything that's going in, it's out. Right? It's not being trapped. So basically, I think what you're saying is correct. Based on this, we could also say the velocity is constant.
Yeah, he said it was also, in other words, it's also fully developed flow.
Fully developed, but yeah.
What does that mean?
So usually when you start, have you seen like a dye drop into a pool of water? Have you seen that's like basically you get like burst?
Yeah,
Okay,
Yeah.
that's why it's starting to, how do you call it, move, or the velocity is like transitioning from 0 to whatever velocity is, so you have an acceleration. So in this phase, when you have v0 equal to 0 going to, let's say, vi different than 0, at the beginning, and this, I don't remember what this distance is, but I think it's called the critical distance. Your fluid is not developed. So your profile is like funky, like this one. But after some distance, and there's something that you guys are gonna study before, you then get a profile, some sort of profile.
Right.
But in this distance, you don't have, you cannot assume, like, for example, that in
That's
this
the
place is Bmax. You cannot say that at all. Like, for example, in this one that I just created, this is Bmax,
Right.
and you don't know exactly what it is. It's like random. So yeah, when we're starting to develop, we're starting to accelerate, it's amorphous pretty much. And that's something that that it's good to point out. Also, something that I did that I recommend you guys to do is that you feel and you see that there's something missing in the homework or in the problem or whatever, add that assumption. Maybe you could get a point or two deducted, but based on that assumption, in this case, like this one, like that we're saying it's fully developed, and the direction is C, whatever, and you say that it's constant, and it's pretty much in line with what we have been doing in class, you can then solve the problem. You won't be saying like, okay, everything's 0. No, that defeats the whole point. But if you see that something is missing, you can add it. Maybe it's a typo, maybe it's something that you had to do, like a leap of faith. And so long as you document that, you should be fine. I used to do that a lot for fundamentals for this class. And I mean, it works. It's better to do and write down always. And this is something I recommend you always. Do not forget to write down. Always write something down, because if you write something down, you can get partial credit. If you don't, you're screwed. Well, not screwed, but you will be deducted the full amount of the question. At least you can do this. Write your system and start developing the assumptions, start working with the equations, and from there you can move on to other to actually solving the problem. So let's continue with this part, the assumption that we created or we derived from being fully developed and from the fluid only moving in the C direction. In that case, we said that the momentum in and out will be,
Equal to each other.
yes, so this will be
0.
correct. Okay. Okay, so the right hand side, done, 0. Cool. But that doesn't mean that it's static. It only means that it's equal to each other. So what's being pushed is the same as what's being pulled. But there could be also, there definitely can be motion in that regard. Okay. So we did the right hand side. Let's do the left hand side. So what are the type of forces that we have, guys?
We have body forces and surface
Yes.
forces.
We have body forces. What's the other one?
Surface.
Yes. So what is a body force? Or what's the one that we have been working with?
Gravity.
Yes, sir. So this guy. We have gravity. Awesome. We know that it's constant, right? It's equal to a G, right? And we have the surface forces. And what are they? Something with a P, an I,
Yeah. The
and you got something with a
shear.
weird T. What is over there? The shear? Shear what?
Shear of XZ.
Yes, sir. Or something else? Is shear the only surface force? What happens when you apply some force
Pressure.
in some area, right? Pressure. How do I write that? I mean, it starts with a negative.
Negative P and like your identity.
Right. Right. But we can use this in order to simplify that expression over there. Right? Something hidden over here. Well, it's not hidden, it's something about one of these guys.
Would it be number 3?
Yes.
You can cancel out like the change in pressure.
That's right. So we get that the gravity plus the shear is equal to 0.
And how come the pressure was like negative value? Everything subtracted.
I'm pretty sure that's the way that you write it in when you have your sigma notation. Sigma is negative pressure, identity matrix plus your tangential forces. But if you want, you can double check and let me know. Because I'm going by memory.
Yeah.
All right. So like convention. Okay. So we have to do some geometry, guys. We have here oopsie. So we have in this side of this right triangle, we have our force, which is this triangle right here. We have the force of gravity, right? And when we want to talk about the force that is acting on this fluid, that's not in the entire force, a portion of it. So what can we use here to relate that side to the hypotenuse? And as a quick reminder, a cosine of some angle alpha is equal to, and the sine, well, let's start with the sine. Sine is equal to the opposite divided by the hypotenuse. Tangent of alpha is equal to opposite of the adjacent. And then cosine is equal to adjacent over hypotenuse. I mess one of those up, please let me. So let's see. We have this angle over here. What will be the opposite and the adjacent? If this is Z and this is X. What will be the opposite of theta and the adjacent of theta? Which side?
Well, I think adjacent is just the force of gravity, right?
Yes. Correct. So we have adjacent. Good. Okay. And what are we trying to look for?
The force in the Z direction.
Yes. Okay. My bad. Yes, which is what part of the triangle?
The hypotenuse.
Correct. So we have something with adjacent, something with hypotenuse. So we could definitely use cosine, correct? Okay, awesome. But first, we have in our thinking box, we have to define what also called what gravity is. Remember? Something else with density. Usually,
That's what gravity is, or
yeah, what's the expression for gravity?
the value, like 9.8.
No, like for example, if we have a vector gravity and we know that it's only,
Oh,
it's like the vector gravity, usually you write it as, for example, it's acting in some plane.
yeah.
This will be equal to a density times the magnitude acting on that plane. No, okay. This will be the magnitude of the vector. Yeah. What I'm trying to do is then decompose this vector into the hypotenuse, which is this side. And we said that we'll be doing it with the cosine. So we know that cosine of alpha is going to be equal to adjacent, which is a FG, divided by the hypotenuse, which is this side that we want. Let's call it GZ. Or the force of gravity in the C direction.
So would it just be rho g cosine theta?
Yeah. Rho G cosine theta. Awesome. Plus over shear. Great. So at this point, we have to we don't have exactly the forces yet. So remember, if we're talking about shear, it's a force divided by the area. So if we multiply by the area, we get force. In gravity, since it's multiplied by density, which is equal mass over volume, we don't really have force exactly. What we have over here is hi. Hey, you can come in.
He's just, he's like, is this a class? He's like, no, we stayed with 4 people.
So something that I forgot to add here is the surface that this shear is working on. And then what we do is the step of dividing by the volume, by the control volume, which is this guy over here. So since it's working in X and Y, the area should be X and Z, X, plane X, Z direction. The area should be Y, X. What would it be?
Wouldn't it be like the x times z?
thing with the delta times the L.
Okay. Okay, so you're saying. So basically, what we're gonna be ended up doing is. I'm trying to get there. So that's the differential we should get. Unless I'm incorrect in my procedure. I was solving this example from the book. Let's back now. We know that gravity that I skipped here. This is going to be multiply times the volume. And then when you divide by the volume, it cancels out. So you essentially get this, right? No.
Sorry, can you say that one more time?
So usually when we write the force of gravity, we have density, the magnitude of gravity, and we add the volume. Because this is acceleration of gravity. And then we said that this density is mass over volume. So when we multiply by volume, we get mass times acceleration of gravity. That's the reason we multiply by volume. Yeah, to get force. But then one of the steps we divide by volume, so we get. And the reason we do that is that we want an intrinsic property, which doesn't change by the amount of mass that we have. That's the reason we divide it by the volume to normalize it. That's I got confused because basically there's like in only one step. That's the reason I'm like kind of like freaking out. But yeah, usually this multiply by the volume, and then in the next step we will divide by that volume. Therefore, we get rho g cosine theta. Oh, which here is in terms of the surface. And the surface that is acting on is z, right, times y, which is this one. So if we have a box, which is acting here, and this box, which is the top of this box, this part is y. So this is like delta y. This part over here is z. So delta c. So usually to get a force, you have to multiply it by the surface, which is delta c times delta y. We divide by the volume, we get this divided by delta x. That was the step that I jumped and didn't quite follow through. My bad. It's been a long day. Okay. So what we know, based on my coordinate system, will the gravity be positive or negative? Making the basically where I have in this is a positive values, gravity is going down. That's something that we didn't catch. So it's negative. So essentially, what we're saying is that the shear rate sorry, the shear, it's going to be equal to the gravity.
How come the gravity is negative instead of shear being negative?
Because the shear is going in the direction of the fluid. It's based on the convention, it's like the C, the positive C direction.
So is gravity not going in the positive Z direction as well?
Not sure.
Yeah, 'cause I thought
Yeah, it's past my bad. It's- It gets negative when we pass it to the other side. So basically shear will be equal to a negative gravity.
So is FFG here, the FFG in the Z direction?
Yes,
What's the gravity for that?
yes, that's also something that I jumped, my bad. Because this, it's only, which is what we care about, and I forgot to say that it's in the C direction. Because there's no forces or anything happening in the X or the Y. Because an inclined plane. But yeah, these are the components in the C direction, you're right. Yeah,
so you said there's no force in the Y component,
yeah, because of the edge effects.
but for the X, would it be like the force of gravity and the normal force? Like if you do like rho G sine theta.
Sure.
But that would be zero still, right?
Yeah, and we basically in order to, we're trying to look is the equation for the shear. It's only relevant in the C direction. All right. We continue, we take we set in class today the limit approaches zero, we have the three,
Would you have like a body component like in the Z and the X direction?
for gravity.
Yeah.
Basically, this cosine is taking care of that.
But wouldn't you still have like a component, like wouldn't that then be the negative, like the negative rho G times the sine of theta for like your X?
For my X, what do you mean? So we have the X.
Yeah, so it would be like the component.
I know what you're saying, and yes, gravity has a component in the X direction. But since the fluid is not allowed to go that way, basically the normal force would counteract that force. Since the liquid can only go through the channel, basically what was talking to Gabe, but I think he was talking about the normal force in this side. It's in the top. Yeah, the only movement that we can get is like going down the incline.
And then you also said isn't there technically like two shear forces?
Yes, we could definitely do two shear forces. The only thing is that we set this. The shear only happens at that point. It's one of the assumptions.
On the homework, let's see. So I don't know if you should make the assumption that the homework has, but
Shear at the fluid air interface can be assumed to be zero.
yes.
You're right.
C0.
You are right. So the one that we are calculating then is this year. And then this will be X. Right? Will be C. That will be X because if it was here's will be delta X. Right?
Just so for assumption 7, it should be TXY equals delta X. I assume. For X plus delta X.
Yeah.
And then I guess how do you know that you're supposed to write like X plus delta X and like how do you know it's in terms of X?
This part.
Yeah.
So as you were saying, it says that we have this magnitude over here, which it says that this length is delta. And it says when shear is equal to it's a delta is 0, so it's talking about this surface.
I'm gonna grind it.
And that shear would still be going in the positive Z direction, or is that going in the negative Z direction now that
It depends how you write it. So as my convention is going down, but you could, if you write it in your diagram as going up, it would then be negative. It's like when you're developing a problem in statics, when you decide how you're gonna set up your diagram, then from there, your equations have to be according from diagram.
But that would change the sign of
Yes, yeah, it would definitely change the sign.
would that give you the correct answer at the end? You chose the wrong direction or
Based on the diagram, no. You only got to be careful about those conventions.
Okay. I'm gonna give the next night, he's like, I can blow myself up. So I have to pay my job for coding.
Keep going. So if we want to integrate this over here, what we should do? So this transport. Something called separation of some.
A variable,
Yes, sir. So what do we do?
put the dy on the bottom, on what? Your dx, so.
Mhm. So what do we get here?
What time is your period end?
3.
At 3. I don't think that's possible.
Yeah.
Like right at 3 according to the registrar?
I mean, I'm gonna like finish a little bit early, so
Oh, no,
you guys
that's
can
good.
set up.
To set up for seminar, so. we'll-
Yeah, not a problem. I won't last the whole session. Don't worry. Of
Okay, thank you.
course. So what? So if we said that this is constant, and we're integrating based on a constant, what would be the integration of? You see, we can get all of this put at the beginning, and will be integral of dx, essentially.
Just be a constant,
Correct. And yeah, that will be a constant. Second.
let's see. or
So we have a C here, yes,
the delta?
or the integration variable is X.
By that by X.
Mhm. So basically, we have this. And we want to integrate like one, essentially.
Right, okay.
And we have something weird here multiplied, but we don't care about that yet. This is a constant, so we will get a
X.
correct.
Yeah, I was gonna say that.
All right, awesome. All right. So we know something about this guy. I think after discussing that, we ended up we're gonna end up
Yeah.
this discussion. Something about rheology. Talked about this somewhere.
That's being plastic.
That's right. So we know that that expression over there is equal to this one.
Yeah. Also, is there, I see that one's the tab at C. And then over here you have X, Y.
Oh, my bad. Let me see. Oh yeah. So we have this. It's going to be equal to a yield stress plus the shear rate all right.
And also the viscosity, right? Times the viscosity.
Yes, correct. Forgot that. So we want to get velocity. What do we do at this point? We already found the first question was to find the expression, which is a general solution for shear. Now the next question is to find BZ.
Maybe like you take the limit. Or no, not yet.
We're trying to look BZ. What is it equal to? Oh, there's something that I forgot. It's gonna make this ways. So one of our assumptions is that we need to end up this event now. But I can send you guys my notes.